There is a liquid that costs less than $3, yet it can do something a $1,000 repair cannot. It does not hide rust, it changes it. At the molecular level, active corrosion turns into a dark, stable barrier that can be painted, sealed, and trusted again. No machine shop, no tools, no expensive coating system, just a cheap powder, warm water, and old chemistry the modern world stopped mentioning. But then something strange happened. The knowledge disappeared. They did not bury this because it failed. They buried it because a permanent rust fix is terrible business for industries that profit when metal dies. Rust is treated like weather, unavoidable, expensive, constant. Every year, drivers replace panels, brake lines, exhaust systems, trailer frames, farm tools, and outdoor gear. Because corrosion is framed as a problem, you can only slow down, never truly stop. That assumption built an entire economy. It shaped hardware stores, body shops, dealership service packages, and the global replacement parts market worth hundreds of billions. The system only works if rust is permanent, in one direction worse, never solved. But history says otherwise. For centuries, metalworkers, tanners, armorers, and military suppliers kept returning to one strange category of natural compounds extracted from bark leaves, fruit rind, and galls. Again and again they noticed the same impossible pattern. Iron exposed to these solutions did not just look cleaner, it behaved differently. Corrosion slowed, stabilized, darkened, and in many cases stopped spreading altogether. Then something strange happened. The knowledge disappeared. Not completely, just enough. It survived inside chemistry texts, restoration manuals, and the industrial formulations with labels the public never reads. And buried inside those formulas was the same forgotten answer, tannic acid. A compound so cheap, so simple, and so effective that once you understand what it does to rust, you also understand why modern industry had every reason to rename it, repackage it, and keep it ordinary. Long before rust became a billion-dollar maintenance problem, people who lived by iron had already noticed something modern industry prefers to treat like a curiosity. It began in the ancient world, not in a laboratory, but in workshops filled with bark hides, smoke, and wet metal. Leather workers in the Roman world soaked animal hides in vats of oak bark liquor to make them tougher, more flexible, and more resistant to decay. The process gave the world the word tanning, but inside those vats another discovery was taking shape. Iron tools that touched the dark brown solution behaved differently afterward. Knives, buckles, hooks, and clamps that normally bloomed orange in damp air came back darker, cleaner, and far less eager to corrode. That pattern did not stay with the tanners for long. Blacksmiths noticed, armorers noticed, military suppliers noticed. Once iron became the backbone of empire, anything that preserved it mattered. Along Roman frontiers, where rain, mud, river crossings, and storage conditions constantly threatened weapons and hardware, craftsmen began using plant-rich extracts from bark and galls as preservation treatments. Whether they fully understood the chemistry did not matter. Observation was enough. The treated metal lasted longer. The rust changed character. Surfaces darkened instead of flaking apart. In a world where tools, fasteners, blades, and armor were expensive to replace, that was not trivial knowledge, it was strategic knowledge. And Rome was only one chapter. Across Persia, metalworkers used tannin-rich plant materials, such as pomegranate rind, to help protect iron and steel from heat, dust, and moisture swings that punished exposed metal. In parts of East Asia, craftsmen working with blades and iron fittings used plant extracts and darkening treatments that were not merely cosmetic. They stabilized the surface. In West Africa, where seasonal rains and humidity could destroy untreated metal with shocking speed, ironworkers developed preservation methods using local bark and pods rich in the same family of compounds. In parts of the Americas, wood and bark extracts with extremely high tannin content were applied to traded iron tools because people quickly learned that imported metal was too valuable to let decay. This is what makes the pattern impossible to ignore. Different civilizations, different climates, Different plant sources, different languages, same conclusion. When many cultures separated by geography and centuries discover versions of the same solution independently, that is no longer folklore. That is field-tested chemistry found the hard way through survival labor and repetition. Then the scientific era arrived and gave the old knowledge a name. In the early 19th century, European chemists began isolating tannic compounds in a purer form and studying their interaction with iron salts and iron oxides. What blacksmiths had learned by experienced chemistry could now describe with precision. The darkening of rust was not magic. The change in behavior was not superstition. A real chemical conversion was taking place that changed everything. Now the old bark vat remedy could move from workshop tradition into naval preservation, restoration practices, industrial maintenance, and eventually military materials science. What began in leather pits and forge yards was now entering the age of journals, laboratories, and formal testing. But the more clearly science explained why it worked, the more dangerous it became to industries built on the assumption that rust must always come back. Because once forgotten knowledge becomes proven chemistry, it stops being an old story. It becomes a threat. To understand why tannic acid matters, you need to understand what rust actually is. Rust is not just a stain. It is an active corrosion product, mainly iron oxides formed when iron reacts with oxygen and moisture over time. And unlike a stable protective layer on metals like aluminum or copper, rust is weak, porous, and unstable. It does not seal the surface beneath it. It traps moisture. It flakes away. It exposes fresh metal. Then the process repeats. That is why rust spreads. It is not a skin. It is a failure that keeps opening new doors. Most anti-rust products are designed around that cycle. They try to block air and water from reaching the metal. Some do it with paint. Some do it with oil. Some do it with wax resin or undercoating. But all of them share the same weakness. They are surface defenses. If the coating is scratch-chipped or applied over unstable rust, corrosion starts again underneath. Tannic acid works differently. Instead of only covering rust, it reacts with it. Tannic acid is a polyphenolic compound found naturally in oak bark, chestnut tea leaves, grape skins, sumac galls, and many other plants. It is one of the molecules responsible for the bitter, astringent character in many plant materials. But chemically, it has another remarkable trait: it binds strongly with iron. When tannic acid is applied to rusted steel, it reacts with ferric oxides on the surface and converts them into a darker, more stable material, commonly described as ferric tannate or iron tannate. That black-blue layer is far less reactive than active rust. It adheres to the metal better, it is more water-resistant, and most importantly, it interrupts the runaway corrosion cycle by transforming the unstable oxide into a more stable complex. That is the real breakthrough. The rust is no longer just hidden, it is changed. This is why the color shift matters so much. When a rusted surface turns from orange-brown to deep blue-black after treatment, that is not just visual fodder. It is evidence that a chemical reaction has taken place. You are watching corrosion lose its aggressive form and become part of a protective interface. And that distinction separates a conversion treatment from an ordinary coating. The coating sits on top. A conversion changes the surface itself. That is also why tannic acid-treated metal often accepts primers and paints better than untreated rust. Loose rust is a terrible foundation. Stable converted oxide is much better. Once the active corrosion is converted and the surface is dry, a proper top coat can lock out moisture even more effectively. In other words, tannic acid is not always the entire finish system. It is the chemistry that gives the finish system a fighting chance. Now there is an important reality check. Tannic acid is powerful, but it is not magic. It cannot rebuild metal that has already been deeply eaten away. It cannot restore structural strength to steel that has become paper thin. It works best when loose scale is removed first and the remaining rust is still attached to the surface. Severe perforation, trapped moisture, layered rot, and hidden internal corrosion may still require cutting replacement or mechanical repair. But within its proper role, the chemistry is extremely elegant. It takes the most unstable part of the problem and converts it into the first layer of the solution. That is why old craftsmen trusted it. That is why restorers still use it. And that is why an industry built on repeat corrosion treatment would rather sell you endless coatings than teach you the difference between covering rust and converting it. Once tannic acid moved from old workshop knowledge into documented chemistry, it created a problem that had nothing to do with science and everything to do with money. Rust is not just a materials issue, it is a business model. Think about how the modern corrosion economy works. Body panels rust so they get replaced. Exhaust systems corrode so they get replaced. Brake lines, trailer tongues, truck frames, brackets, tools, fasteners, outdoor equipment, farm hardware, marine fittings and undercarriages all create recurring revenue when corrosion is treated as inevitable, temporary, and never fully solved. Every product category around rust assumes the same thing: you will be back. Back for another coating, back for another repair, back for another part. A treatment that is cheap, unglamorous, and difficult to monopolize does not fit that system well. That is the core of the suppression story. Not necessarily secret meetings in dark rooms. Something quieter, more durable. Market logic. Tannic acid is a naturally occurring compound. That means it is hard to own in the way corporations prefer to own a solution. It can be extracted from common plant sources, purchased in bulk, mixed simply, and understood by anyone willing to read beyond the label. It does not create the kind of dependency that high-margin industrial systems create. It does not need a dealership package, a subscription model, or a branded mythology around advanced protection technology to work. So industry did what industry usually does when a cheap answer threatens an expensive market. It absorbed it. Rebranded rust converters began appearing with technical names, aggressive packaging and premium pricing. The chemistry was dressed up in solvents, additives, marketing language and proprietary terminology. Oxide conversion system, advanced corrosion encapsulator, industrial metal stabilizer, different words, familiar reaction. In many cases, the old chemistry never vanished at all. It was simply hidden inside products the public was trained to experience as specialized and expensive. That move solves the business problem perfectly. The public still pays more, the chemistry still works, and almost nobody realizes the original method was never exotic to begin with. This is how useful knowledge disappears in the modern world. It is not always banned. It is not always censored. Sometimes it is just relabeled, marked up, and pushed so far inside commercial language that ordinary people stop recognizing it. And once that happens, the market wins twice. First by selling you the cure, then by making sure you never learn how simple the cure really was. Here is the part that makes the whole story uncomfortable. The method is almost embarrassingly simple. Start with tannic acid powder and warm water. Mix a small batch until the liquid looks like strong black tea. Before applying it, remove any loose, flaky rust with a wire brush scraper or coarse steel wool. You do not need to grind the metal to a polished shine. The goal is not to erase every trace of rust. The goal is to remove the unstable material and expose the bonded corrosion underneath so the tannic acid can react with it. Then brush, wipe or spray the solution onto the rusted area. Wait. Within minutes the color begins to change. Orange-brown corrosion darkens toward blue-black as the surface converts. Let it dry fully. If needed, apply a second coat. Once cured, the surface can be sealed with paint oil wax undercoating or another protective finish depending on the job. That makes it useful for far more than car parts. Axes, machetes, trailer frames, tent stakes, cast iron pans, truck underbodies, outdoor tools, gate hinges, steel brackets, shop equipment. The exact finish may change, the chemistry does not. And that is the scandal hiding inside the whole story. One of the cheapest rust treatments on Earth is also one of the oldest, easiest, and most adaptable. So the truth is not that humanity never discovered a real answer to rust. It did. It discovered it in bark vats, forge shops, naval yards, restoration benches, and chemistry labs. The answer was never missing. It was simply buried beneath branding markup and an industry that makes more money from recurring corrosion than permanent prevention. Tannic acid does not sound futuristic. That is exactly why it is so easy to overlook. But now you know. If you made it this far, you now understand more about rust conversion than most people ever will. Subscribe and share this with someone who deserves to know the truth behind it.